Hello. We continue our discussion on the differential equations, and this is the fourth installment to the series on differential equation, and theoretically this will be the final part to it. We'll be also dealing with a few numericals for better understanding of the topic. Now, we had already discussed about the uh, linear differential equations of the second order, starting from the first order then over to the second order. Now we'll generalize that for the homogeneous equations of the nth order. So let's get started with that. So first up, we'll be taking the homogeneous nth order linear differential equation with constant coefficients. So in this case, we represent the equation in this manner. Let's say we have P naught as the constant over here in the first element, dny dx to the power n, followed by P1 added to it with dn minus 1 y divided by dx to the power n minus 1, and it continues up until the last two terms being Pn minus 1, the coefficient, multiplied to dy by dx, plus Pny, and that is equal to 0. Now this can be written in the form as P naught d to the power n plus P1 d to the power n minus 1 plus, and we are quite familiar with this kind of an expression because we had considered this in our second order differential equation, where we know that the d that we are representing over here is simply equal to d by dy, that is the differential, not dy but dx, d by dx, the differential with respect to x. And also for d squared and the other terms that we have, they are of the order of the power that we have mentioned over there. So d squared will be d2 over dx squared, and similarly dn over dx squared will be the d to the power n differential operator. Now this equation can further be shortened with a notation where we are taking f of d to be equal to the bracketed term that we see over there, that is p naught d to the power n plus p1 d to the power n minus 1, and it carries on till pn minus 1 d, followed by that the last term over there is pn. I had taken it as p naught, so it is pn. So that's the notation that we are using, f of d. So that means the above equation that we have over here, that goes to f of d operating on y to give us the homogeneous relation with the 0 on the right hand side of the equation. Now this f of d can be factored. Well, it can be factored in the form as follows, that is f of d will be equal to, we keep the first term as such, that is the constant coefficient p naught, followed by the factorized terms, that is d minus m1 d minus m2, and it carries on up to d minus m n minus 1 term multiplied to d minus mn. And as we take it to the above equation, what we obtain is that f of d operating on y, so I just multiply or put the y over to the right hand side of the equation that I've just written, and I add the y over to the right hand side there as well. So this would equate to 0 considering the homogeneous relation or homogeneous equation at hand. The p naught, that is the constant coefficient that has been multiplied, that can be taken over to the other side, divided to 0, and that would vanish. So what we are left with is relation d minus m1 d minus m2 and so on, d minus m n minus 1 term and d minus mn being the last term, and that would equate to 0. So we have the what we call as the characteristic equation. So this boxed term that I'm having over here, that gives me the characteristic equation for the nth order differential equation. Obviously a homogeneous equation, and we have the roots of the equation to be equal to m1 m2 through over to mn minus 1 followed by mn. These are the roots of the characteristic equation. Now, in case it may seem a bit puzzling to you how we got into this factorized equation, I would like to show you a few things that we have done in order to get to that process, and followed by an example which will help you understand this in a better way. So I hope so it does. Now this that I'm marking over here, extra term. So this now the equation that we see over there, we can put the value of x over there, let us say as e raised to the power z. So what that gives us is that z is equal to the log x to the base e, and then we have d upon dz to be represented as d. So if we consider dy over dx, then we may write it as dy over dz multiplied to dz over dx. We can do that. This is in the form of a chain rule, and dz upon dx will obviously give us 1 upon x, and we have the left term, that is dy by dz as such. So what that leads us to is that this dy by dx is finally coming out to be 1 upon x dy by dz. So finally we have dy by dz, or yes, dy by dz, we keep it like that. Dy by dz will be x times of dy upon dx, and dy by dz, as you know, d by dz is taken as this d, which acts on y to give us x times of dy by dx. So that's more or less the case with d y by dz, or d of y, which is giving us x times of dy by dx. Now if we consider the double derivative, that is the second order derivative of y with respect to x, that is d2y upon dx squared, so that is equal to d upon dx dy over dx, and that will lead us to d upon dx, and the value that we have just obtained, which is 1 upon x dy by dz, which is the value for dy by dx that we just obtained in the line before above, and that again leads us to the derivative of the first term followed by the second term kept as constant, then the derivative of the second term with the first term being constant. 1 upon x is constant, so d2y over dz squared, it's actually yes, dz squared, and we can have another dz upon dx. So what we have done is it would have been dz and dx over there, but what we have done is we have taken dz again and multiplied the dz at the top. So that gives us, that's a shorthand thing that we have done. You can refer to the previous line for whatever has happened there. Now from this, what we obtain is that we can take 1 upon x squared. Now this right hand term that we see dz upon dx, that will be equal to 1 upon x for sure. So this is equal to minus 1 upon x squared dy by dz, plus this is 1 upon x as it is, so this is d2y upon dz squared, and the last term that we see dz upon dx, as you know, is simply 1 by x1 over x, because it's the logarithmic thing that we are taking into account. So from that we can take 1 over x to be common in both the cases, 1 over x squared, that is, we can take that as common. I am writing it over here for clarity. So this is 1 upon x squared can be taken as the common term from both those elements, and what we are left with is the second term being positive can be written at first, that is d2y over dz squared minus dy over dz, and this is equal to 1 upon x squared. As you can see, this is the double derivative of y with respect to z, so this is capital D squared minus the single derivative, that is the first order derivative, so that is d only. So what we have, or what we are left with, I can take this separately. So this essentially is equal to 1 upon x squared, and we have a d square minus d multiplied to y. So that's d2y over dx squared, and we have dy over dx. So we can continue like this with x cube as well. So any guesses for x cube? I'll write it onto the next page. So that finally results in the previous one, that is, we'll do the third derivative as well. So that has resulted in x squared d2y over dx squared to be equal to d square minus d whole acting on y. And finally we can also say the similar case for x cube d, the third order derivative, that is d3y upon dx cube, to be equal to d times of d minus 1 times of d minus 2. You may go on to think that if this is the case, then why would we just use the m terms? We could have just taken it in the way of 1, 2 and 3 instead of m1, m2 and m3. Well, we'll see an example for that. A numerical approach will help us to understand it in a better way. So considering the case where we are taking an equation of the form, supposedly is in the second order form, and we have x squared d2y upon dx squared minus 2x dy over dx minus 4y, and that is equal to 0. Now what that results in is that we will be following the same procedure, and from that what we get is the first term, that we have x squared multiplied with the second order derivative of y with respect to x, that will directly lead us to this form, that is d square minus d, or we can take the d out, it will be d minus 1. So we'll write it like that: d times of d minus 1 acting on y minus 2 times of the second term is again of the form x times of dy by dx will be simply d, and finally the last term being 4 only, and that all of that is acting on y with the right hand side being 0. We can take the y out from the first part. So we have the equation to be of the form d square minus 3d minus 4 gets multiplied to y, and that is 0. And if we go on to factorize this thing, what we get is this is d minus 4 times of d plus 1, and that is equal to 0, and we have therefore have 4 and 1 to be the roots, and d minus 4 d plus 1 multiplied together, they form the characteristic equation exactly in the form that we saw in the previous segment that we were discussing, and which was this right there. So this expression that we see is a final form of what we have been provided with right from the very beginning over here. So you need not be confused. We have the numerical example to support our approach to the given equation. Now, rewriting that equation from the previous page for reference, what I get to know is that each of the operators which they will commute with one another, because we have the 0 on the right hand side. So each operator acts on the expression to its right. The complete expression will be 0 if the result of the first operation is 0 as well. And it is to be noted that any one of the n operators can be written immediately before y, and it then follows that n solutions of any one of the n equations can be obtained as follows, where we are generalizing it as d minus mi for I can be anything ranging from 1, 2, 3 right up to n terms for the nth order differential considered, and the solution will be of the form for that L of y is equal to 0, which means L is equal to that bracketed term that we have over there, and that will be equal to d upon dx, that is acting on y, of course, and that is taken, we are just rewriting that equation over here. So this is dy by dx minus mi times of y, and that leads to 0, and it has a solution of the form y is equal to e raised to the power mi times of x, the general solution. So for n number of solutions, the nth order equation will have n solutions. So for n solutions, what we get is that we have e m1 x e raised to the power m2x, and it continues e raised to the power mnx. So these are the solutions. Now in case of they are linearly independent, and we have m1 to be not equal to m2, supposedly not equal to m3, and so on up to mn, if they are not equal, then the general expression of the general solution of the equation can therefore be written as the combination of this, that is c1 e raised to the power m1x. Remember, c1 and c2, and likewise there will be the arbitrary constants which will be multiplied, the constant coefficients, that is, and it continues up to cn added to the rest of the terms mnx. And in case out of those n roots, if we are having r roots as equal, and they are all equal to m, then the solution, the general solution, can be further expressed as y is equal to c1 followed by c2 multiplied with x, and it continues up to cr, and that is multiplied to x raised to the power r minus 1. So those are the r terms that are having the same root, that is m. So this is e raised to the power mx. This is for the r terms. And then finally the other terms follow, where cr plus 1 e raised to the power m r plus 1 times of x, and that again gets added to the rest of the terms as in the previous case, right up till cn e raised to the power mn times of x, and this leads us, or this gives us the solution to the, or the general solution to the nth order differential equation in the homogeneous form. And now we move over to the inhomogeneous condition, where we will be discussing about the particular integral. Now, as for the inhomogeneous equation, the only difference being that we have an fx on the right hand side which has a certain value. So what we get, the equation is obviously of the form p naught times of p naught being the constant over here, dny divided by dx to the power n plus the n minus 1th order, which is dn minus 1 y divided by dx to the power n minus 1, and it follows right up till pn minus 1 dy over dx, and finally pn y, and that is equal to fx. Now fx here has a value, it's congested over there, I write it in the next line. So fx on the right hand side, fx being not equal to 0. So again we take it of the form f of d acting on y, and that is equal to fx on the right hand side. Now f of d, as you know, is what we have been taking and right from the previous case. Now the operator that is going to act is now of the different form, where we have f, if we are to multiplying by an operator 1 upon f of d, we will be getting 1 upon f of d multiplied to f of d y on the left hand side, and 1 upon f of d giving, or multiplied to fx on the right hand side. So these operators will obviously cancel out each other, f of d in the denominator and f of d at the top, so they will be cancelling out. We are left with y only on the left hand side, and onto the right hand side we have f of d fx. This f of d is what we term as 1 upon f of d is what we term as the inverse operator. It's more like the, if f of d was the differential form, inverse operator is of the form of the integration, but it has certain rules of operation that we'll be discussing right away. So the rules of working of this inverse operator can be laid down as follows. Now when this f of 1 upon f of d, that is when it's acting on a function e to the power ax, the result is e to the power ax divided by f of a. And if it were to operate on another case where we have e to the power ax multiplied to a function of x, let us say vx, then that will result in e to the power ax as in the previous case, but further it will have f of d plus a multiplied to Vx. And then in the third case, if we are taking the double form of it, that is f of d squared, and that's acting on cosine of ax plus b, then onto the right hand side that we obtain is cosine of ax plus b divided by f of minus a squared, and that is if f of minus a squared is not equal to 0. So f of minus a squared must not be equal to 0. If it is equal to 0, then we have a separate condition. We take the third derivative over there. Then if this acts, that is 1 upon f of d squared is acted upon sine of ax plus b, then we end up with sine ax plus b divided by f of minus a squared, the condition being the same, that is f of minus a squared must not be equal to 0. Now once again, in case of the inhomogeneous linear differential equation that we see, it will comprise of both the parts, that is the complementary function as well as the particular integral. So we must take both the cases into consideration. First of all, we'll be obtaining the homogeneous case where we have the YH, as we have been discussing right from the previous videos, and then we'll be obtaining the particular integral for taking the YP that is a factor of the given y. So y is equal to yp plus yh, that is the particular integral as well as the complementary function. So we'll have two forms in this in case of inhomogeneous. In case of homogeneous, obviously we do not have the particular integral, that need not be considered. Now in case, as I said, that if this thing fails, then that means f of minus a squared is 0. In case f of minus a squared is equal to 0, then what we must take into account is the first derivative, that is the solution is of the form, instead of just this case, that is sine ax plus b divided by f of minus a squared, we will be getting x times of sine ax plus b divided by the first derivative form of this, that is f dash or f primed of minus a squared. And in this case, obviously we have taken f dash of minus a squared is not equal to 0. In case that goes to 0, again we will consider x squared sine ax plus b whole divided by f double primed of minus a squared, and it continues so on. So let me just write that. In case we have f prime of minus a squared, that is the derivative of that, to be equal to 0, then we'll have the solution to be of the form x squared sine ax plus b, and because that's x squared, this will be double primed minus a squared, and it continues so on. From that you can make out the form or in which we will be taking these things into account with the values going to 0. The next step that is to consider is to multiply an x and then take the derivative, the higher order derivative in the denominator. So that's more or less the case with the nth order differential equation. We have discussed both the homogeneous as well as the inhomogeneous form or inhomogeneous conditions, the solutions that are associated with both of them, and it will only be proper for us to try a numerical which will help us understand this topic in a better way and cover the most of the things that we have discussed. So let's take an example which is going to help us. So if we are to solve, that is obtain the solution for a given equation of the form d2 or d squared minus 4d plus 4 acting on y, and on to the right hand side this is an inhomogeneous differential equation of the order 2, so this is x cube e to the power 2x, and for that, first of all we'll be obtaining the complementary function. So as for the complementary function, we take the left hand side, that is d squared minus 4d plus 4 to be equal to 0, and that gives me d minus 2 whole squared to be equal to 0. So finally we have d to be equal to 2 and 2. So that means the complementary function here would be equal to, that is yh we can say, is equal to c1 plus c2x times of e to the power 2x. Remember, the roots were of the form m e to the power mx, so instead of m we have obtained the root to be 2, so e to the power 2x. That is the complementary function. Now in case of the particular integral that we must obtain, that is yp, so that will be equal to 1 upon fd that we have, and that is acting, well, if you see, this is of the form, the second form that we have discussed right over here, that is e to the power ax times of vx, the second form over here, that is this one. So that leads us to, so we write that first, that is x cube e to the power 2x, is it? Yes, x cube e to the power 2x, so that is going to be in the form 1 upon f d plus a being the factor multiplied to e to the power ax, that is the coefficient of x in the power of e, the exponential. So this is e to the power 2x, so this is f of d plus 2, and that multiplied to the equation that is over here, e to the power 2x 1 upon f of d plus 2 multiplied to vx, so vx is x cube. Now with this, what we get is the e to the power 2x remains over here on the left hand side. Now what was f of d in the first place? So this was f of d. Now f of d plus 2 is going to be, we are going to add a 2 to the d's, so e to the power 2x, this is 1 over d plus 2 whole squared minus 4 times of d plus 2 plus 4, and all of that acting on x cube. So this will give me, we expand that term, so e to the power 2x 1 over this entire term over here, that is d squared plus 4 plus 4d minus 4d minus 8 plus 4, all of that multiplied to x cube. So the 4 and 8 cancel out, the 4d cancels out. It's a fairly easy one. So we have 1 over d squared x cube, and as we know, this is, as I mentioned, this is just the integration form, instead of the derivative taking the inverse operator. So this is e to the power 2x. The first integration, because this is double integration, so first integration will lead us to x to the power 4 upon 4, and that is 1 by d remains as such, and then the second integration will lead us to e to the power 2x remains as such. The second integration will lead us to 1 over 4 remains there, and x to the power 5 over 5 for integration of x to the power 4, and then we are left with e to the power 2x, x to the power 5 over 20. So this is the particular integral. As we know that y, finally the solution is equal to yh plus yp, so this is going to be equal to yh that we have obtained over here, that is c1 plus c2 times of x e to the power 2x plus e to the power 2x times of x to the power 5 over 20. We can take the e to the power x as the common term, so e to the power 2x taken common, c1 plus c2x plus x to the power 5 over 20. So this is the final expression of the given, or the final solution of the given inhomogeneous second order differential equation. We have solved it in a way for the generalized nth order differential equation, taking taking the case of particular integral into consideration, the rules that we have just studied. We'll be doing a few more videos on the numericals related to the differential equations for better understanding of the topic. So for that, you can wait and try out these things that I have mentioned, or I have gone through in these videos in the series. Till then, thank you for watching.